what's called vcol. It's the volume of the space where particles exist that can actually hit the wall. Divided by the overall volume times n would be the number of particles that could possibly hit it. The volume of this segment, vcol, is just this distance right here times the area. So I have Vx times time times the area of this, I'll call it case of x, over the overall volume times n. And we have to do one other thing, is the fact that as these particles are moving, that it's just as likely to be moving to the right as it is to the left. So this might be the number of particles within a particular region here, but half of them are going in the wrong direction. So n call number that will collide would be half the particles that are in that region. So therefore, the force that is being applied in the x direction. From over there, it's 2 times the number that will collide, which is 1/2 Vx T A x over V n times mvx divided by time. And notice that time disappears. Or cancels out, probably a better word than disappears. Consolidating, I get n, the total number of particles divided by the volume, the total volume, so the number density, times m Vx squared times a. And really, on average. Notice I dropped the subscript for the a there. Let's just make it a cube. Now, if we think about it, if I have a particle, so the velocity of a particle is Vx I hat plus Vy j hat plus Vz k hat. What's V squared?
Vx squared I hat plus.
You went too far. You're doing a dot product with itself, so there's no direction to find my answer. So you said Vx squared
plus Vy squared plus Vz squared.
So if I'm looking at averages here, that the average value of V squared would be equal to the average value of Vx squared plus the average value of Vy squared plus the average value of Vz squared. And because these things are moving randomly, the average value of Vx should just be the average value of Vy, which should just be the average value of Vz squared. That squared is supposed to be inside. So, and this is average notation. You familiar with it? You are, you're not? Okay, I can express,
I've only ever seen that used for vectors.
It translates in quantum physics to expected value, but that is equal to that, which is equal to x average. Therefore, I'm making the claim because of the random nature of the particles that the average value of v squared is just 3 times the average value of vx squared. So I can now take my equation right there and make a little substitution, so I now got 2/3. Sorry, I have to go from over there. So I got 1/3 particle number density m a v squared. This is the mass of a single particle. I'm going to introduce the 2 right there, 2/3 n over v times a times 1/2 m v squared. So I multiply by 2 and 1/2. So what is this?
Kinetic energy.
It's going to be average kinetic energy. So we end up with, this was the force. Equals force. I'm going to divide by the area. Force over area is equal to 2/3 n over v times average kinetic energy. Force divided by area. What is that? Flashback to chemistry.
Pressure.
Sorry?
Pressure.
Yes. So that's pressure. Capital P, it's not power, it's pressure this time. So pressure is 2/3 this numeric density times the average value of the kinetic energy. If I multiply both sides by V, by the volume there, this should start looking somewhat familiar to you if you've had chemistry. And maybe if you've had physics. So I have the pressure times the volume is equal to 2/3 times the number of particles times the average kinetic energy. What's pressure times volume equal to? I assume you've both had chemistry.
Yeah.
PV equals,
nRT.
that's the one. Which is 2/3. All right. This n is the number of moles. This n is the number of particles. What is a mole?
6.022 times 10 to the 22nd. 23rd.
All right. So n, the number of moles, is just the number of particles I have divided by Avogadro's number, which is 6.02 times 10 to the 23rd. 6.022?
Yeah.
Sure. All right. So if I make that substitution here, I get big N over NA is RT is equal to 2/3 big NK. Well, my n's cancel out. big ends cancel out. And let me solve for K. So my average kinetic energy is just 3/2 times this R over NA times T. And that is something else. That is known as Boltzmann's constant. So R is the gas constant, ideal gas constant, I forget. I haven't had chemistry since early 80s.
I believe so. I can, I think it's.
All right, well, it's R over Avogadro's number. So this now becomes the average value of the kinetic energy is 3/2 times Boltzmann's constant times the temperature, and that's in absolute terms in Kelvin. Did you find it?
Yeah, that's correct.
Gas constant, ideal gas constant?
Yeah,
Either?
it's ideal.
Ideal, all right. So we now have a relationship between average kinetic energy and temperature. So when you rub something, so they talk about energy being conserved, but if I push something across the table, it will slow down, or if I push it and let it, and then take my hands off, it will slow down because of friction. Well, that energy goes into the table molecules, which changes the temperature. And on that note, any last moment questions?
One random,
Good.
less related thing. I noticed you used uppercase I for impulse.
Instead of J?
Yeah.
I flipped back and forth depending upon the semester. I think I started with I this semester, so I stuck with it. Did I use J earlier?
I just noticed that I've seen J everywhere else I've looked.
Okay.
It's generally.
Yeah, when I was doing it just then, I thought, oh, it's capital J. And I thought, then I went back and forth. Yeah, I probably should use J. But I didn't, so there. But it is a good note, if you're looking elsewhere and they use a capital J, just recognize that I'm using I. Vector. I without the vector symbol is moment of inertia. All right, clock says it's time to go now.
What chapter was this last thing?
Let's see. This last bit was chapter 20. Because usually, we're ahead of where I usually am at this point. So I don't get to this every semester, but when I have little time and I'm doing thermodynamics, I usually do this first because, to me, I think this is really neat, the fact that we now have a relationship between average kinetic energy and temperature. So that's why I started with it. The book just happens to take it in chapter 20.
Thank you very much. See you on
Well,
Wednesday.
See you Wednesday.